Hello, my name is Sydney, and today in this video I will be telling you about the conservation of angular momentum as it applies to some real-world examples, as well as the study of kinetics of rigid bodies. Momentum is also known as a mass in motion. It is a vector quantity, meaning it has a magnitude as well as a direction, and can be either a mass moving with a linear velocity in translational momentum or with an angular velocity, combining translational as well as rotational momentum. Another important term when talking about momentum is impulse, which is a change in momentum, which can occur through a change in direction or a change in speed. As there are two different types of momentum, these same principles can be applied to both. Dealing with momentum, we can apply and analyze the conservation of momentum. In both linear as well as angular momentum, we can see that it is conserved in both phases analyzed, before and after a change occurs, unless an impulse or external force affects the system. This is only true without the presence of forces such as friction, air resistance, or some other direct force on the system being applied. In the case of angular momentum, it would cause a moment, while in linear, it would be a linear force, both allotted over a designated period of time. Similarly, as linear momentum is measured by multiplying mass by velocity in a specific direction, angular momentum is measured by an angular velocity occurring in either the clockwise or counterclockwise direction, multiplied by a mass moment of inertia taking at the center of the body of rotation. This is also noted as I. The sum of all entities within the system is taken with each moment of inertia calculated. It is important to note that momentum is conserved when the change that takes place is internal, which we will see in the example in which final angular velocity is estimated. Throwing a frisbee is an example of angular momentum, therefore air resistance that actually slows it down at the end of the throw is an example of impulse and external forces coming into the system. Spinning in a chair is another example of angular momentum taking place about the person in it as the center of rotation. The example that I will illustrate and calculate out will be determining and comparing the angular velocity of me spinning in a chair before and after changing the radius of rotation of a pair of dumbbells being held outward. Analyzing the system before and after this internal change takes place, we can see that the dumbbells, when held outwards before, experience a velocity that is tangential to the path of rotation. Since the system moves at a constant angular velocity, these linear velocity variables within the equation can be replaced with angular velocity of the system multiplied by radius, or omega r. Each dumbbell also has its own mass moment of inertia in which it experiences the rotation of the system about at the measured radius. Following my arms being brought inwards, the after phase, the radius will decrease, which can help us predict that the final angular velocity calculated will be larger. In this case, this is omega 2. The angular velocity occurs in the same direction both before and after, because the rotation in the counterclockwise direction does not stop or change. Only my arm movement will change. The first part of the calculation includes determining the mass moment of inertia of the person or chair system. In order to determine it, I pictured it as a rectangular prism and estimated the length and width measurements as I fit within a rectangular box. Since the center of rotation is not placed directly along the z-axis, the parallel axis theorem was applied to move the mass moment of inertia to be placed at the center of rotation, or the center axis through the person and chair. In order to find dz, which is needed for this, we applied the parallel axis theorem using a distance formula with x bar and y bar as the coordinates used. And now for the necessary calculations. Since the shape is assumed to be uniform, it can be assumed that the center of the y-axis is the midpoint of the A measurement. Similarly, x bar is the midpoint of the B measurement. All measurements are converted to feet. As shown, A equals 1.75 feet and B equals 2.25 feet. As a result, x bar is 0.875 feet and y bar is 1.125 feet. Additionally, since we are using English unit system, the masses of the system need to be divided by g, or 32.2, in order to convert to slugs. Plugging numbers into the equation, the mass moment of inertia about the z-axis, knowing that dzz equals 1.425, the mass moment of inertia is 3.893 slugs feet squared. Then applying the parallel axis theorem, the mass moment of inertia of the person-chair system is found to be 15.57 slug feet squared. The mass moment of inertia of each dumbbell is found by separating it into 3 separate cylinders and determining the radius and mass of each section to determine its mass moment of inertia along the z-axis. It's important to note that dumbbells are held vertically in the simulation so that the mass moment of inertia occurs through the center of each cylinder along the z-axis, and therefore the parallel axis theorem does not need to be applied. The radius of the center cylinder, section 2, is found by dividing the circumference measured with a measuring tape and dividing it by 2 pi. Additionally, since you can't break down the weight to get the mass of each section, it is found that weight is distributed evenly to the 2 outside sections, which would be 1 and 3. So the 5 pounds total were broken down as 2 pounds on the ends and the center being 1 pound. The total mass moment of inertia is found by adding the individual ones of each section together, therefore resulting in a dumbbell mass moment of inertia to be 1.025 times 10 to the negative 3 slugs pound squared. Radius 1 was measured with the tape measure to be 2.25 feet, and radius 2, when I bring my arms in, is 0.29 feet. We also took back just all the variables that we calculated to condense it into one place. Additionally, testing how fast I could spin without using my arms for leverage, it was estimated that the initial angular velocity spinning in the chair was half of a revolution every second. This measurement was converted to radians per second by multiplying it by 2 pi. Plugging all variables into the equation, omega 2 can be calculated and isolated to the right side. Therefore, our final angular velocity found is 3.45 radians per second, or 0.549 revolutions per second. This supports the initial prediction that the angular velocity would increase if the radius of the rotation is decreased. It's also important to note that the angular momentum of each dumbbell is multiplied by 2, since 2 are used in the total system. The final angular velocity, like we said, is greater in turn. To further the analysis and support for the conservation of momentum, I'm going to perform this experiment with 2 pounds as well. It can be assumed the change will be much smaller since the weights are lighter, therefore the change in speed will have a smaller effect because the massive system itself is rotating with an entire person and chair. In order to perform this second calculation, we can note the differences between the system when we use the smaller dumbbells. We can see that all variables will remain the same except for the mass of the dumbbells and the mass moment of inertia of the dumbbells to be plugged in for the final calculation. These are noted with a star, as well as the final angular velocity that we will be solving for after moving the arm inwards to be a different value. The same process is followed to find the mass moment of inertia of the dumbbell by breaking it into 3 separate cylinders and finding their individual values to add them together to find the total mass moment of inertia of the dumbbell. Once again, the equation for the cylinder equals 1/2 mr squared, so I broke the dumbbell down to get each section's mass and radius. Since this weight of the total dumbbell is 2 pounds, and it's still evenly distributed at the ends, I assumed that the ends would be 0.75 pounds in sections 1 and 3 near the ends, and only 1/2 pound along the center cylinder at section 2. Again, in order to find the radius of section 2, the circumference was taken using a measuring tape to be 4 inches and divided by 2 pi to find the radius. All mass measurements were converted to slugs by dividing it by 32.2 and the length measurements to feet by dividing it by 12. As found with the heavier weights, this equation accounts for the axis of rotation being directly through the weight, so the parallel axis theorem does not apply. The total mass moment of inertia of the dumbbell is found to be 2.728 times 10 to the negative fourth slugs feet squared. Solving for final angular velocity, all necessary variables are noted, with both radii and initial angular velocity being the same, as well as the mass of the person and chair and its respective mass moment of inertia. The mass of the dumbbell, being 2 pounds, is converted to slugs for calculation. Then, as you can see, plugging everything in and isolating omega to the right side, we can find that the final angular velocity, or omega 2, equals 3.26 radians per second, also 0.520 revolutions per second when it is converted. Although the change is smaller than when using the 5-pound weights, there is still an increase in the angular velocity from its initial 0.5 revolutions per second, therefore highlighting the conservation of angular momentum. There is a bit of room for error in this estimation, especially around finding the mass moment of inertia of the person-chair system and the dumbbells. In order to find mass moment of inertia of the person, we assumed a uniform shape, while it is actually an irregular shape. Similarly, the weight distribution was assumed in the dumbbells because I was unable to isolate the sections. Another thing to consider is that work is done in order for the person to bring the weights inwards. In the form of chemical potential energy used to power muscles, it is an external force present on the system, and it was not accounted for. Overall, though, we were able to successfully analyze angular momentum and its conservation.